Hello all, electric flux, field lines and the flow. The electric field lines due to a point charge are radial with the charge at the center. Of course, there are infinitely many field lines. We draw only finitely many representative field lines. There is no reason why field lines due to a point charge should be more crowded in one direction than the other. Therefore, the angular separation between the consecutive field lines must be the same. The field lines may be compared with the vectors representing the flow of liquid. The field lines are not crowded in any one direction than the other. This means that the flow of the field lines across the spherical surface is uniform in all directions. Counting field lines. How many field lines pass through the spherical surface? It's infinite as field lines pass through each point on the surface. However, one may give a finite measure to the number of field lines. The field lines pass through every point of any imaginary surface in an electric field. One therefore cannot count the infinite number of field lines passing through the surface. Tubes of field lines. Let's collect neighboring field lines to form groups of field lines. These groups form tubes of field lines. The tubes are not necessarily cylindrical. They may have arbitrary shape depending upon field line pattern. One can count the number of tubes passing through an imaginary surface in the electric field. The total number of tubes of field lines passing through any given imaginary surface in an electric field is called electric flux. Let's call the tubes of field lines as simply the field lines. Electric flux density. Consider a spherical surface of radius r centered at the charge q. Let phi be the number of field lines passing through the spherical surface. That is, phi is an electric flux through the surface. As field lines are radial, they pierce through the spherical surface at 90 degrees. The number of field lines crossing the surface at 90 degrees per unit area is called flux density. Electric field intensity. An electric field E due to a point charge Q at a point P, a distance r from the charge, is given by Coulomb's law. An electric flux density at a point P is defined as the number of field lines passing normally, that is perpendicular to the surface, per unit area through an imaginary small surface around point P. For the field lines to pass normally, the surface around the point P must be a part of the sphere centered at the charge, as the radial field lines are perpendicular to the surface of the sphere. Let phi p be the number of field lines through the small surface of area AP around the point P. The electric flux density is given by electric flux density at a point. The radial field lines are uniformly distributed in all directions. This means that the ratio of flux to the surface area at any point on the sphere is constant and is equal to the ratio of the total flux through the spherical surface to area of the sphere. That is, the flux density at P is equal to phi, that is the number of field lines, divided by area 4 pi r square of the sphere. Comparing electric field intensity and the flux density. For a point charge Q, the electric field intensity at a distance r from the charge is the electric flux density at a distance r from the charge is E is equal to q upon 4 pi epsilon naught r square. Now we multiply by phi at the numerator and denominator. And then we write q upon phi epsilon naught separately. Then this quantity represents flux density. For a given point charge q, the quantity q upon phi epsilon naught is constant, and therefore we can write electric field as constant time flux density. And thus we conclude that the electric field is directly proportional to flux density. Electric flux density at a point. To calculate flux density, one divides the number of field lines phi by an area A of the surface, which the field line pass through normally at every point on the surface. Now consider an arbitrary surface such that exactly same field lines pass through it. The field lines will not pass normally through any arbitrary surface. Such surface is not used in finding flux density. Field line and field intensity. Electric field intensity at a point is directed along the tangent to the field line at that point. This means that the field line passes through the surface normally wherever the field intensity is perpendicular to the surface. Field lines through surface. In general, field lines are not perpendicular to the plane surface at every point on it unless the field lines are parallel. Therefore, one cannot use plane surface. Electric flux. An infinitesimally small surface is always a plane surface. The field lines passing through this surface are so close to each other that they appear parallel to each other as they pierce the surface. One can now adjust the orientation of the plane so that the field lines pass normally through it. Recall that an electric flux density at a point is defined as the number of field lines passing normally per unit area through an infinitesimally small surface around that point. An electric flux d phi through perpendicular area dA around the point P is thus: electric flux through small plane surface around a given point. An electric field at a point P is E bar. We wish to find flux through a small plane surface dA around the point P. The flux d phi is given by. Recall that the above formula applies only to the surface which the field lines pass through normally, that is, when the field E bar is perpendicular to the surface. In general, the electric field may not be perpendicular to a given surface as in the present case. Therefore, we cannot use this formula. We denote the orientation of the surface by an arrow perpendicular to the surface. This arrow defines area vector of the surface. The angle between the electric field and the area vector is theta. Now we construct a plane surface perpendicular to the electric field such that exactly the same field lines pass through it as those through the original surface. That is, the flux through the two surfaces is the same. An arrow normal to the new surface represents area vector dA dash of the new surface. The angle between the original area vector dA bar and the new area vector dA dash is also theta. Let's shift the new surface to make its bottom edge coincide with that of original surface. It can be shown that the angle between the two surfaces is also theta. We calculate flux through the new surface as follows. An electric flux d phi dash through the surface dA dash is now flux density is proportional to electric field. We can choose the constant of proportionality as 1 and write flux density equal to E. And then we have d phi dash, the flux, equal to E times dA dash, where we have replaced flux density by electric field to obtain d phi dash equal to E dA dash. Let L be the length and B be the breadth of the original surface dA. Similarly, let L dash and B dash be the corresponding quantities for the new surface dA dash. We have d phi dash equal to E times L dash B dash. As the surface dA dash is rectangular, its area is length times breadth. We complete the triangle as shown. Using trigonometry, we find from the figure L dash equal to L cos theta, B dash is equal to B. Substituting for L dash and B dash in this equation, we get d phi dash equal to E LB cos theta. D phi dash equal E LB cos theta. LB is the product of length and breadth of original area, which we denote as dA, and we get d phi dash equal to EDA cos theta. EDA cos theta is defined as the dot product or a scalar product between the two vectors, the electric field vector and area vector. The flux d phi through the original surface dA is the same as the flux d phi dash through the new surface dA dash. We thus obtain d phi equal to E bar dot dA bar. We replace d phi dash here by E bar dot dA bar to obtain the flux d phi through the original surface as the scalar product between electric field vector and area vector. Electric flux through the surface of arbitrary shape. The surface of arbitrary shape is divided into n very small surface elements so that the surface elements can be treated as plane surfaces. We calculate flux through individual surface elements using the formula and then add to obtain flux through entire surface. Consider any surface element, say of area dA1 bar. To start with, let E1 bar be the electric field there. The flux d phi 1 bar, d phi 1 through this surface element is E1 bar dot dA1 bar. Similarly, we have flux d phi 2 through dA2 bar, flux d phi 3 through dA3 bar, and so on. The total flux phi through entire surface is given approximately by adding flux through all n individual surface elements. That is, we write E bar dot dA bar for each flux through surface elements. The above equation gives approximate flux. From calculus, we must go on reducing the size of surface elements indefinitely to obtain true value of the flux. This amounts to increasing the number n of parts to infinity. The sum above then becomes integration. And this is the formula that gives us total electric flux through a surface of arbitrary shape. Thank you for watching the video. Please like, share and subscribe.